The modern highway, outgrowth of the motor age. In every part of the country, roadways such as this, smooth and durable, lead the traveler to his destination and speed the movement of materials of every variety. Rolling along over the long, straight stretches, often flanked by eye-filling scenery or rounding graceful curves, the traveler seldom thinks of the engineering skill and construction technique utilized in these ribbons of concrete and steel that make possible the miracle of modern transportation. Steel, dramatically flowing from the open hearth furnace for processing into many forms and products, today is an indispensable material in the construction of the modern highway. Oddly enough, a great portion of the steel used remains forever embedded in the paving, where it serves to give the roadway permanent strength and durability. Some of it, however, is visible as in overpasses and bridges. In the construction of highways, steel serves also in the complicated and amazing road building equipment characteristic of the work to be done. The toughest jobs are accomplished in stride, and roads can be cut through to provide the most advantageous routes. In the old horse and buggy days, the course of a road was frequently dictated by the location of a bridge. This was the era of the covered bridge, picturesque and substantial, but today a symbol of the past. As the automobile brought higher speeds of travel and more traffic, the type of bridge was gradually changed to meet the new conditions. Through the use of steel, rivers are now spanned without deviation from the prescribed course. Modern bridges, designed with an eye to beauty as well as strength, are a part of the highway. Early concrete roads were simply cast slabs without inner reinforcing, but the traffic soon became too heavy for this type of roadbed. The lesson was learned that highways, like other types of construction, can only be as strong as the materials used in building them. Steel has the needed strength and adaptability, and the steel industry has developed through research many different products for use in highway construction. The steel for such products first appears in the solid state in the form of ingots. Here's a 6-ton ingot starting on its way to be rolled into a wide flange structural shape. Cast in conventional form from molten steel out of the open hearth furnace, the ingot is reheated in a soaking pit furnace to a temperature of about 2200 degrees Fahrenheit when it is ready for rolling in what is known as a blooming mill. At this temperature, the form of the ingot is readily changed by passing it through the rolls which exert pressure on it. Each time the ingot passes through the mill, the rolls are brought closer together. Thus, each pass reduces the cross-section and increases the length proportionately. The mill is equipped with manipulators which turn the ingot so it can be rolled on all sides, thereby improving the internal structure of the steel. The mill operators have complete control of the operation of the rolls and the movement of the ingot through the mill. After the steel has been passed back and forth between the roll a number of times, the rough form of the eventual cross-section begins to be apparent. The steel is at a temperature high enough to permit rolling in subsequent mills without reheating. After being rolled down in the blooming mill, and before it is passed on to the next operation, the ends are cut back to sound metal. The long steel shape is then sheared into lengths convenient for rolling in the structural mills. Each of these lengths is passed back and forth through the various roll stands which constitute these mills. First through the roughing rolls, then through the finishing rolls. As in the blooming mill, each pass results in a reduction in size and an increase in length. The last step before cooling is to cut the 200-foot member to commercial lengths by means of a hot saw. rolling process has been completed, from ingot to finished product in about 10 minutes. Many types of rolling mills, differing in size, though similar in character, are used to turn out a wide range of steel products for highways. For the demands of the road builder for these products are as varied as the terrain upon which he must construct your highways. Where the soil is not firm enough to support the roadway, as in marshy areas, the wide flange H piling is very helpful. These long steel sections are driven down through the soft earth till they rest on the bedrock many feet below. Other steel members, including the reinforcing steel, can then be joined by welding or otherwise to the top ends of the piling. And the whole thing will be as solid as if the roadway were built right on the bedrock itself. Another form of piling, steel sheet piling, is manufactured in a variety of cross-sections and plays an important part in the construction of a modern highway. This versatile material is also used for permanent retaining walls and to give extra strength to structures such as bridge abutments. When it is necessary to construct a concrete pier in the bottom of a river, a temporary cofferdam of sheet piling is called for to hold back the water. Steel sheet piling is the ideal material for this purpose. One pile interlocks with the next, and the joints are accurately mated to reduce water seepage to a minimum. It can be easily driven and often can be withdrawn and used again. With the temporary cofferdam in place, construction proceeds within its protecting steel walls. Where your highway must cross the larger bodies of water, steel rarely comes into prominence. Here, where a main highway spans the Susquehanna River at a point where it is about a mile wide, we find an example of what the steel industry means to this great business of highway construction. Actually, construction of a highway bridge starts almost as soon as the site is selected. It has to, because there's a tremendous amount of design and engineering work to be done. The topography largely determines the type of bridge to be used. Every piece of steel in it is cut to strict specifications at the steel company's fabricating works and assembled into sections of convenient size for transportation. These sub-assemblies are scheduled to arrive at the bridge site in the order in which they are needed. Here, as elsewhere, steel serves not only to support the roadway, but to hold together and reinforce the concrete pavement. Everybody knows about famous steel structures like the Golden Gate Bridge, the George Washington Bridge, and the Chesapeake Bridge, but few people think of them as what they really are, highways over water. Not just connecting links between two highways, but part and parcel of the highway itself. From the standpoint of actual mileage, of course, most of a highway is built on the ground. And even in the first steps of construction, steel enters the road building picture. Road building today is no pick and shovel operation. For yesterday, the roads more or less followed the contour of the land. Today, the shape of the land must be made to conform to the plan for the highway. Ridges must be cut away and gullies filled in. Steadily, over the years, the jobs have become bigger and tougher. And to meet the challenge, heavier and more specialized steel road building machines have been developed. One such machine is the drag scraper. It scoops the dirt off the high spots, carries it along, and deposits it in the hollows in one operation. Power shovels of many standard and special types dig away the earth and expose rock formations. These obstructions were spotted previously by the surveyors and now must be removed to bring the highway to the established grade. With modern equipment, it's more economical to blast them out of the way than to go around them. Air-powered drilling machinery bores into the rock, making holes for dynamite. The drill itself is hollow, and the blast of air forced down through the center blows the rock dust out of the hole. It's a faster operation than the old way and gives a truer hole for the explosive. After the required number of holes have been drilled in the layer of the rock, The dynamite is carefully tamped into place. And when the area is cleared, after the dust settles, men and machines dig in again, scooping up the broken rock. In this type of work, equipment really takes a beating. Wire rope, a few hundred pounds of it installed on a 30-ton shovel, is the steel member on which the whole mechanism depends. Wire rope is strong and resilient, must withstand the highly abrasive atmosphere of the construction project, and must not fail when subjected to repeated flexing over small shivs and drums. As manufactured today by Bethlehem Steel Company, wire rope gives outstanding service under hard usage. Modern highway design does not tolerate grade crossings. In most cases where a railroad or another highway is encountered, either underpass or overpass is provided. In bridge construction, concrete piers are reinforced with steel bars. The protruding ends are left long enough to be bent over and tied into the bridge deck. In either piers or pavement, a firm bond between steel and concrete is assured by the deformations rolled into the bars. Bethlehem Steel Company maintains reinforcing bar fabricating shops in all major highway construction areas. Road building materials are stocked at these locations. As needed, reinforcing bars are cut to length and bent to shape. In any mass of concrete, certain lines of stress develop, and the bars are carefully bent to follow these lines so that they will bear their full share of the load on the completed structure. Used in all kinds of concrete work, reinforcing bars are one of the most important steel products in modern highway construction. This heavy structural member built up in one of the company's fabricating works is intended for use in an overpass. Getting a member of this size to the place where it's going to be used is sometimes difficult. Often the building site is many miles from the railhead, and this means trucking over unimproved highways or temporary rough-graded work roads. Specialized machinery does the job with seeming ease. Cranes also had to be moved to the site ahead of time. As with any construction, there is much planning and preparation before the final sections can be added. When the piers are ready, the cranes are there and the lift is made. With precision and complete assurance, the girder is carefully set into place. It's 100 feet long and weighs somewhat over 30 tons, yet handling it is all in the day's work to the modern road building crew. Road building is a continuous operation. While work is going on elsewhere, the right-of-way is steadily being cleared of all obstacles and made ready for the paving crew. In preparation for the concrete, steel paving forms are staked in place along each side of the lane to be paved. Besides providing a retaining wall for the concrete, the forms are used as tracks on which some of the paving machinery moves. These forms are laid upon the subgrade, which previously had been prepared to sustain the load specified for the paving in the roadway. A well-drained subgrade also prevents the resultant heaving action of the paving if it is subjected to freezing temperatures. An odd-looking gadget called a scratch template gauges the exact depth needed for the concrete, and the big job of preparation is finished. Now comes the paving, and here too steel steps in. There are several important items that won't be visible when the highway is finished because they'll be embedded within the concrete pavement. Here is a simple but effective steel device that demonstrates how steel industry research has solved a road building problem. This device, the keyway, is one of many steel specialties that not only conserve time and labor, but more important, add to the strength and durability of the pavement. The keyway and a companion piece, the center joint tie hook bolt, are quickly and easily assembled on the job. Attached to the paving form, the keyway projects into the concrete when it is poured. When the form is removed, the keyway thus formed provides a groove or mortise into which concrete from the adjoining slab will flow, forming a tenon. Where keyway and hook bolt are not used, The weight of moving traffic tends to depress one slab where it meets the other along the center line of the paving. In time, this causes cracking. So, by using the keyway and enclosing the hook bolt in the concrete, an interlock is created, and the two slabs are tied together, sharing the load. Displacement and subsequent failure are prevented. After the paving form is removed, the hook bolt that will anchor the adjoining slab is simply threaded into the embedded sleeve nut. Another important aid to good road building is the Bethlehem dowel unit. Whenever concrete is poured in a continuous operation, a means must be provided to control the cracking that may occur because of stresses induced by heavy loads and temperature changes. Otherwise, there's no telling where the cracks will appear. That is why there are joints provided between sections of the concrete. Any cracks that occur will then be where they are wanted, that is, where the dowel units are placed. When the steel dowel unit is not used, the natural cracking of the concrete is uncontrolled. Temperature changes increase the cracking, destroying the overall strength of the concrete. Because the slabs are not tied together, the pressure of heavy traffic causes them to sink down into the subgrade. And when water seeps down through the widened crack, pumping begins. The inner structure of the highway begins to deteriorate and eventually to crumble and fall apart. When the steel dowel unit is used, the faulting is controlled and held to a minimum. Also, pumping is prevented, thereby preserving the integrity of the subgrade. The concrete stays strong and firmly in place. The dowels hold the slabs in line under temperature changes and also provide a means of transferring the weight of heavy traffic from one slab to the other. Dowel units are economical to ship by rail or truck. They nest easily, and because they are light and compact, they can be assembled either right on the job just ahead of the pavers, or if more convenient, at the contractor's stockpile. The steel plate fits snugly, and the oblique slots keep it from floating in the wet concrete. Used in this combination, the unit becomes a contraction joint. Another important use of the dowel unit is in an expansion joint. Concrete naturally expands and contracts with changes in temperature. Also, solid material sometimes gets down into the joints and takes up space. In time, if nothing is done about it, the slabs will buckle. By inserting a cork or fiber filler instead of the steel plate, a means is provided to absorb the pressure, and the highway remains intact. With the fiber filler in place, the dowel unit is ready for its job in an expansion joint. The filler allows for the expansion of the concrete due to temperature changes as well as its growth as it ages. It also prevents foreign material from entering the joint. When the dowel unit is placed in position, a temporary cap is installed over it. This is to protect it against the first rush of concrete in pouring. The cap will be removed before the concrete hardens. In addition, short lengths of tubing are slipped over one end of each dowel, alternating between one side of the joint and the other. Thus, working space is provided within the concrete for the longitudinal movement of the slabs. Thermal changes affecting the concrete cause it to expand and thereby exert pressure on the filler, which forces the sealing compound slightly above the joint. When the pressure is relieved, the compound retracts to fill the void, thus maintaining its sealing property. Concrete paving today is a highly organized assembly line operation. The dry ingredients, sand, stone, and cement, are carefully measured elsewhere and brought to the job by a fleet of trucks. Each batch is dumped into the dual drum paver, which is really a mixer on wheels, capable of handling up to 72 batches per hour. On single-lane paving, the teamwork of men and machines up to an average of 3,000 feet of finished paving in an 8-hour day. The mixer has 2 drums. This design enables the paving operation to proceed without delay, because while one batch is being mixed, another is being transferred to the bucket. The moist concrete is dumped on the roadway just ahead of the spreader. This way of working is called the strike-off method of paving, which means that the first course of concrete is roughly leveled off at the proper height for laying in the reinforcing steel, which is in the form of steel mats. This hinge type is a product of Bethlehem Steel Company. These steel mats are fabricated at a number of Bethlehem's plants and mill depots. The special hinge makes it possible to handle the extra wide mats easily. Because they fold to 8-foot widths, they can be loaded compactly and shipped on trucks or railroad cars. They require a minimum of field storage space, and when folded for shipment, clip base, preventing racking of the mats. As the mats arrive on the job, they are laid out ahead of the pavers, ready to be placed over the first course of concrete. The procedure for laying the second course of concrete is the same as for the first. The same machinery is used and all operations are repeated, except, of course, the spreader is raised to the new level. In double-lane paving, the slabs may be poured as wide as 24 feet. Most highway steel products are designed to fit either paving method, but in double-lane paving, single bars of reinforcing steel are used in place of hook bolts. These bars provide a center tie between the 2 halves of the wide slab. In double lanes, the center joint is formed by cutting after the concrete is poured. This gives the double lane slab the appearance of 2 lanes. Naturally, a double width lane requires twice as many steel mats as a single lane. In both types of paving, the hinged mats are simply unfolded and laid out side by side. Just a simple arrangement of steel rods crisscrossing the roadbed, but when the final course of concrete is put in place on top of them, this strong mesh of steel locks the whole thing together. This is highway steel in one of its simplest but most effective forms. The spreader now goes to work on the concrete mass. This action serves not only to distribute the concrete evenly between the forms, but also agitates it so as to maintain the proper distribution of the ingredients. Whether the road builders are using the double lane method or paving 1 lane at a time, the basic procedure from here on is the same. Following along behind the spreader is a battery of finishing machines. Each machine has 2 oscillating members called screeds, which scrape off the concrete at the level of the paving forms. This operation is repeated by a second machine, which closely follows the first. The action of the screeds not only establishes the final grade level of the finished highway, but also consolidates and improves the structure of the concrete near the surface. The last machine in the line is the longitudinal floater. But before this goes to work, the temporary installing caps over the dowel units are spotted and removed. The function of the longitudinal floater is to fill in and smooth out any waves or depressions left by the previous machines. As its name implies, the oscillating motion of this machine is perpendicular to that of the other machines. Thus, the concrete surface is smoothed out in both directions. Then the rough highway is ready for the rear guard of hand craftsmen who follow the road building machinery, craftsmen who put a final finish on the road surface. Any slight wrinkles left in the wet concrete are smoothed out by the hand float finisher. Other men follow with strips of burlap on a wooden frame, giving the surface the proper texture for traffic. Craftsmen finish the edges along the paving form and smooth out the concrete along the joints. There are several ways of curing concrete. In this instance, burlap is placed over the fresh paving and kept moistened until the concrete is set or cured. This prevents the concrete from drying out too fast. When the pavement is completely dry, the joints are sealed, which helps to prevent moisture from getting down into the subgrade and is the final step of the paving process. This section of finished highway, with its backbone of steel, will be utilized by numberless trucks and passenger cars during its lifetime. It is therefore not surprising that the same type of construction is being used in airport runways, which today need to be more durable than ever before. Planes are bigger than they used to be, they fly faster, and they carry heavier loads. Concrete has been found to best withstand the effects of impact and the terrific heat generated by fuels, such as are used in jet planes. And so the steel and steel products that make today's highways possible also serve today's airways by strengthening the airport runway. No highway is really completed until it's equipped for safety. Wherever there's a curb, fill, or other danger spot along the road, there's a need for protection. Safety beam guardrail is a strong and effective highway guard. The steel posts to which the beam is attached arrive on the job cut to length and properly punched. The special post-driving equipment mounted on a truck drives them to uniform depths. Steel guard posts are easy to align, and they last longer than other types. The beam sections have a shop coat of paint and are ready for assembly when they arrive in the field. Safety beam guardrail is cold formed from strip steel and then punched and sheared to specified length simultaneously. The channel construction gives it unusual strength. After they're formed and punched, the guardrails are finished by being cleaned and given their protective coat of paint. One bolt fastens the rail to any type of post, and a splice assembly made up of a splice plate and bolts secures the beam ends to make one strong continuous steel rail. The flared ends of the rail add to the appearance of the job. Safety beam guardrail gives ample protection because the continuous steel beam tends to absorb impact and distribute it over a wide area. A finish coat of white paint completes the installation, making the safety beam visible night and day. The safety beam guardrail adds to the streamlined appearance of the highway. Another highway safety guard, adaptable for use with wood, concrete, or steel posts, is the cable guardrail. The shape and depth of the offset bracket gives this guardrail exceptional shock-absorbing qualities. The anchor rod is attached to a concrete block buried in the ground. Turnbuckles maintain tension in the cables. This is still another packaged unit of the steel plant. The addition of right-of-way fencing gives further protection to the motorist and to the property owner. Its hinged joint construction contributes to its flexibility, which is as well as its installation. Here is a protective web of steel hung on its supporting self-fastener post, a finishing touch of steel for the modern highway. And so your highway is completed and steel has entered into every phase of its building. Steel equipment was used in clearing the roadbed and in pouring and smoothing the concrete. Steel buried in the paving and piers reinforces and strengthens them. Steel makes possible the necessary bridges and overpasses. Steel guardrails and fencing are protection to the traveler. In all parts of the country, highways that are so important and necessary to our civilization are being built today with steel. Highways that will serve for many years to come. They must be strong and smooth and able to carry the great caravan cars and trucks and trailers that make up present-day traffic safely to their destination. The modern highway is truly the open road, the broad, pleasant avenue leading to business and creation, and future portends in highway planning and construction.